In this question, this is a question of angular SHM. We have a uniform meter stick suspended from a point which is 10 centimeter away from the end of the stick. This is the point of suspension. We need to find out the time period of small oscillations about point of suspension. Now we generally know that for small oscillations the motion of an object is SHM. Let us check it out. Let us first prove that this motion is actually SHM, and let us find out the time period of the SHM. Now let us take a general object. Let this be suspended about this point. Now in case of angular SHM, if you need to prove that it is SHM, you have to follow a similar pattern to the linear motion type. In this, you displace the object from the equilibrium position by a small angle theta, and then you prove that the net resultant torque, restoring torque, is equal to c into theta, where c is some constant. If you can prove such a thing, then you can write the time period to be equal to 2 pi root over I upon c, and you can also prove that it is angular SHM. So in this question, let us first prove that. Let this be the equilibrium position of this body. This means that the center of mass is lying along this line, because the point of application of the gravitational force is the center of mass of the object, due to which this is the point of equilibrium, because the net torque acting on the object is 0 in this case. Now to disturb the object from the equilibrium position, what we do is that we displace it from the equilibrium position by an angle theta, due to which the line joining the center to the center of mass gets displaced by an angle theta, and the point of application of mg becomes here. Now let this distance be d. Let this distance be d. Now we see that there is definitely a restoring torque, because this mg tries to rotate the object back towards the equilibrium position. So the torque due to mg is the restoring torque about this axis. So if we write the torque of mg, this comes out to be mg into the perpendicular distance of the line of action of force of mg from the axis, that is equal to, this was d, this is d cos theta, therefore this is d sin theta into d sin theta. Now it is mentioned small oscillations. For small oscillations, sin theta can be taken to be theta, therefore this becomes mgd into theta. This is also the restoring torque. Therefore we have proved that the restoring torque is equal to some constant into theta. Therefore we can write the time period to be, therefore we have proved that it is angular SHM, and the time period of angular SHM comes out to be I about axis of rotation upon mgd. Now we know that this is the axis of rotation and this was the axis passing through center of mass. We can also write I axis to be equal to ICM plus md square by parallel axis theorem of finding out moment of inertia. Therefore the formula for time period becomes 2 pi root over ICM plus md square upon mgd. You need to keep in mind what these terms mean. This is the moment of inertia of the object about its center of mass. D is the distance of the point of suspension from the center of mass, and after feeding in these values you get the time period for the small oscillations of the object. So this is a general formula that we have derived for any object, and this is also known as the time period of a physical pendulum. And you should always remember this result in the future. So when we apply this formula in our given question, we already know that this will be a angular SHM, because this is a simple body of physical pendulum basically. Therefore the time period comes out to be 2 pi root over ICM plus md square. This was the center of mass of the uniform stick. Therefore d is equal to, this is a meter rod, therefore d is equal to 40 centimeters. D comes out to be 40 centimeters, and moment of inertia about the center of mass for a rod is equal to ml square by 12. Here L is equal to 1 meters. So we feed in the values here, 2 pi ml square by 12 plus mg into d, that is 40 by 100. Sorry, here we get a term of md square. mgd comes in the denominator, md square upon mgd. On substituting the values here we get, before that we see that m cancels, so we can write this as L square by 12, L is equal to 1 meters, 1 upon 12 plus d square, d was equal to 40 centimeters, that is equal to 40 by 100, 40 by 100 whole square upon m cancelled upon g into d. D again is equal to 40 by 100. On solving this we get t is equal to 1.55 seconds. So the answer for time period for this physical pendulum comes out to be 1.55 seconds. The important thing is that you should remember this formula for a physical pendulum in the future.